Okay, so your programming test number 1, the guide and practice question have been released, and all the information is there, so please read it over. If you got any doubts about part of the PDF, the guidance or policy, let me know. I just want to mention to you guys for section X, just one thing. I'm going to also update the semester calendar on the lecture side pretty soon. So if you look at the time over here for section X for you guys, it's going to be the lecture time for 1 hour, Thursday, not Tuesday. All right, please be careful, right? Watch out. And February 27th. All right, that's the only thing I want to clarify. And I'm also going to update the semester calendar PDF pretty soon, just to make sure they're consistent, right? But it's fixed. All right, so let's look at other reminders. During the reading week, next week, I'm going to host our office hour, maybe in person. If you want to make it to the campus, speak to me about the course material, anything, you're welcome to. If you really want to, let's say, zoom in during those office hours, you may just drop me an email beforehand. I'll try to see if I can speak to you, but I still give priority to your fellow students showing up in person. Hope that's understandable. And your split array harder, the solution tutorial video is already there. I'm pretty sure that's going to help you on the programming test number 1. And assignment number 2, assignment number 1, right? Don't forget, assignment number 2 is due, I believe, at some point soon, right? I'll send you guys a reminder on the same day, but I definitely don't want to wait for too long. That one there is also covered in your programming test number 1, right? The required study and the recommended study, they're all there. And TA will still be available through email, the same email, and also notes template, everything, right? Guys, any question? All right, good. Let me just mention one more time. For today, I just want to make up the time lost due to my problem from last time. I want to extend the lecture for just 10 minutes. Around 6:50, okay, around 6:50, I'm going to take a short break for 1 minute. If you have to leave, no problem. Just catch up the recording maybe later. But I'm going to go until about 7 p.m. today, after the short break. All right. Just make sure we're covering the same thing for both sections. Let's do a quick recap, and then we'll see. Right? I do have some interesting stuff for us to discuss about linked list. Okay. So last time we basically talked about number 1, how to do the add first, just by looking at the code itself. It's only using variable assignments, object creation, if then else, so constant time. But to understand the logic, you really have to trace in about the different cases over here. Especially you can see we have a special case over here. If the current size is actually 0, that means we're adding the first node into an empty list. In that way, we had to make sure the tail is also equal to head. This is something that we criticize about singly linked list. You really don't want to deal with so many edge cases explicitly. So when we move on to doubly linked list, there is a way to actually make this code much simpler, which we'll see by the end of today, right? So you can keep that in mind. That's also one thing that's good about using doubly linked list. Right? Also make sure the size is kept in sync with everything else. And you guys can also look at the lecture recording to see how we can trace the code line by line, right? Tracing is also very important. And then we talk about 2 linked list operations here, not the Java code, but Visual Sketch. And we also derive the asymptotic upper bounds from there. So we talk about remove first, and also we talk about add last. And one thing you want to really pay attention to is for remove first and add last, they both only take constant amount of time. It's only about changing the references for the relevant nodes or creating some new nodes. So very efficient operation. But as soon as you talk about something like, let's say, remove the last, that's something I will also recap. This is the most notable operation you want to watch out for singly linked list. Because once we get to doubly linked list, the story is going to change because we're trading space for time one more time, right? We'll get there. Okay, just keep that in mind. All right, you guys can look at the different steps for these 2 operations. I will expect you guys to know how to implement them in Java, right? We spoke about all the detailed steps already. So you should know how to translate them into Java code. And we'll talk about how we can get access to the middle of the list. All right. So the middle of the list will be specified by some index I. And in the case of the singly linked list, I can be as large as maybe second last node, which will be n-2, or the last node will be n-1. Either way, it's going to cost you linear time, as we spoke about. So this is not an efficient operation for you. And one thing for you to also to test yourself for your understanding. if we try to go to doubly linked list, is accessing the middle going to be improved? That's something we'll see today as well, right? Also the question you're going to ask yourself. And also make sure you can do tracing. And we talk about how we can add a node at a particular index I, right? So the most important thing I want you guys to make sure you review when you review the nodes is like this. We are trying to add into index I. So if you look at the existing chain of nodes, we got index I, we got index I minus 1, which is the previous node. We know that getting to this previous node is expensive. It's going to be linear time. We spoke about it. And also you got to remember, in order to insert one node in between right here, you want to make sure you understand I minus 1 remain the same. This will be the new index I. And this will be the new index I plus 1, as if we are shifting to the right by one position. All right, just keep that in mind, okay, when you review. And all the relevant operations, we also spoke about them in detail last time, so you can take a look. Okay. All right, and then we talk about how you can insert into the middle. That's basically where we stop from last time. So I would like to continue from here. Before that, guys, any question from last time? Any confusion about singly linked lists in general? So I think today the pace could be slightly faster than before. I do assume a little bit more familiarity about the link structure. Today I'm going to finish off a few more examples on the singly linked list, and then we'll dive into doubly linked list. I really hope to finish everything today. We'll see, but I wouldn't rush. If you really find it too fast, slow me down. That's definitely fine. All right, let's now take a look at this example here, inserting to the middle. All right. So we are basically talking about add at a particular index over here. If I happen to be 0, that means you want to add at the first node, which we traced already, the first node, right? If you see what we did last time, if I did 0 over here, that means add first. What we didn't really trace completely was, what if I want to add maybe 2, right? In this case, I want to add to position 2. 2 here happen to be the end. Well, in general, what if I want to add to the middle, right? You want to think about what's going to happen. Let's complete the tracing and analyze the asymptotic upper bound at the end. So let's say we want to add to position 2, index 2, which will be here. And we want to add a new node called UNA over here. That's the element, right? So what we do is we know that it's not going to satisfy this special case because the list is not empty. We already got 1, 2, 3, 4 nodes already. So we want to add first, add here, right? So what's going to happen is, if you think about the indices, sorry, let me just get it organized right here. All right. If you want to add at index 2, that means right here. Index 2 is here. That means index 1, which is index 2 minus 1, right? 2 minus 1, like I minus 1. This one here is now going to point to here, so this will be index 2. What used to be index 2 is now going to be index 3, exactly how we illustrated. All right. So the first step right here is to get node at I minus 1, the previous node. This is the most costly step that's going to dominate the asymptotic upper bound, right? So that's what we did last time. Node before is going to be exactly here. Because 2 minus 1, right, it's going to be index 1. Okay. What about second step? For the second step, right here, we're going to create a new node. Right, let's now write it down. So I'm going to create a new node right here that is going to point to a singly linked node, right? So we got a node here. And we got elements, we got next, right? The element E is UNA over here, right? Elements, and then we got the string UNA here, next. And you can see the next will be node before that get next. All right? So that means for this node, we're going to set its next to be node before the next. We're going to set it to be there. All right? So now we're going to set it just right here. So that this is now index 2. And this will now become index 3, right? You can see that right away. So this will be index 2. And now this one will be index 3. All right? Exactly how we discussed it. And then let's do one more step to fix everything. So now node before that set next is going to be the new node, right? We're going to make sure it's also set properly. So node before is right here. The next, rather than pointing to here, is now going to point to this new node right here. And also we're going to update the size. Okay, so the size rather than 4 is now going to be 5. So these are the complete steps, right? You can also trace by yourself. What about the structure afterwards? You can think about it's going to look like this. So what used to be index 1, still index 1. But this now will be index 2, and followed by index 3 right here. All right? And of course, the code itself doesn't really update the tail. You may have to do as well. But you got to make sure you extend the code and update the tail also properly. Right? That's something I can leave to you. Right? So that's about insert to the middle. And you just got to remember the asymptotic upper bound is going to be determined by this first step, which is going to figure out where is the previous node. There, in general, it can be very close to the end. In that way, it's going to be linear. All right? So overall, it's going to be linear. Right here. All right, any question about this method here? All right, we're good? All right, sounds good. So now we are done with this method here. Let's see what's next. Inserting to the middle, right? And what about the corresponding operation for the array? If I actually want to insert to the middle of the array, I also need to shift everything to the right by 1 position, right? So that's also linear. So inserting to the middle doesn't really matter if you do it in a link structure or in an array structure. They will just be equally bad or equally inefficient, just linear time. All right? If no further question, let's now look at another one here. What if we want to remove from the end? So this is the remove last operation I was talking about. So this arguably is the most important operation for you to really see why it would be so inefficient for singly linked list. Let's take a look. So we want to remove, we're not creating any new node, just want to remove the last node, the current tail, basically. All right? Now the question is, we already got tail attributes there. We got head, we got tail, we got size. Is the tail attribute itself enough to complete the algorithm? Right? Apparently not. Once we see the diagram, we'll see. All right? Take a look here. All right? Removing the end. I'm only going to trace maybe one line with you just to get an idea. And afterwards, you can try to do others as exercise, right? So let's now see the setup here. So I got basically these lines of code. I build the structure here, Tom, Mark, Alan. So in the reverse way, Alan, Mark, and Tom, right? And then I just want to trace one single line right here. I want to remove the last. And you guys' exercise will be try to trace these two remove last as well to see how they should be visualized and how they should work. That's the important exercise, right? Let's focus on the first one to get an idea. All right, so currently the size, you know what? The diagram should be extended a little bit to really make sure it's accurate, right? So you can think about this guy here. Okay, the size currently is 3. We got 3 nodes. And also we got a tail, right? That's complete. What we want to do is we want to remove this last node here. But the problem is if we want to remove this node, that means we need to set this particular guy's reference next to be null. But do we know what this one is? Not really, because we only know that this guy here is the tail. But what about this guy? We don't have any attributes storing that. So the only way we can get its reference is by computing it using a loop. All right? That's very important for you to see. All right? So this one over here is the second last node. That need to be computed. And we don't have a direct reference to it. And you cannot just say tell the previous. There's no such thing like a previous reference. Would be the case for doubly linked list, but not for singly linked list. Let's now trace it to see exactly how we do it, right? So here, the current size is not equal to 0, it's 3. So we are not going to do this, all right? Also, the size is also not equal to 1. Also, we don't need it, all right? So these two edge cases, we don't satisfy it, we can skip. So what I will do is, let's now do 1 here, 2 here, 3 here, and then 4 here, right? We got 4 steps. Let's execute them one by one. Step number 1. The second last node is going to be computed using getNodeAdd, right? We want to calculate the previous node. Right? Size minus 2 is going to give us the index for the second last, right? Size minus 1 is the index for the last node. So size minus 2 will be second last. So what we'll do, so this one here is going to be big O of n, right? You can see that it's accessing the middle, right? So what this one will do is we're going to create a reference right here, and then that one there is called second last node. Right? The current size is simply equal to 3. So 3 minus 2 will be 1. So 0 and 1. So that's exactly this node, right? That'll be the first step. The second step, once we got a second last node, everything else will be straightforward. Second last node that's set next should be null. So second last node that's next should be null, right? So that's the second step. So this was the first step. All right, that one's done. And then we're just going to update the tail. So tail, rather than pointing this node that's being deleted, it should be this second last node. It's not a new tail. So what I'll do is, rather than pointing to here, it's now going to point to right here. So this will be step number 3. And step number 4, we also got to make sure we update the size from 3 to 2. Step number 4. So after all these, what we have is a structure that looks like this. So we got the head pointing to here. Okay, maybe a little bit thinner. We got a head pointing to the first node, and then the second node, and then that one there is simply pointing to null. That'll be it. Right? Any question about this? Okay, make sense? All right. Important exercises for you guys will be to try to trace maybe remove last and remove last, 2 consecutive remove last after that, to see how the list structure is going to change. Important exercise. Okay. All right. Any follow-up about this? All right. And of course, the running time, as we said earlier, is going to be dominated by step number 1 right here. So it's going to be big O of n. Also a very inefficient operation because it involves going to the second last node. No way around, linear. All right, 2 more, and then we can conclude about singly linked list, and then we can move on to doubly linked list. So these 2 exercises over here, it's just about if you want to insert after and insert before, how would you do it? Okay. And these 2 over here, we're assuming that we are basically getting the node reference right here, node here. So give me one moment. Let me just show you where you can see that on the slides. So we are done with removing the last. That one is done. Oh, sorry, right here. If you look at slide number 30, so that's what I'm talking about, right? So we got these 2 operations over here. In the slide, it simply got different steps over here describing in English. But I'm going to tell you how you can think of each step visually. And your job will be to translate them into Java. Right? Similar exercise. I'll rely on you. Let's take a look at one by one. Okay. For insert after, right here. So what we get as input is some node n. Okay, you can see there's a node n. So n is pointing to somewhere in the middle, right? Somewhere. What we want to do is we want to insert a new node maybe after that. All right? That one there doesn't seem to involve anything about previous node. Agree? All you got to do is you got to make sure there might be some next node right now. If I want to insert a new node, you got to make sure I goes this and then go this, basically. Right? That's what I need. So what I can do is let me just put a little bit more in context right here. Let's say we got another node here at the moment. That one is simply just n.next. Right here. N.next. N.next might be null if the n is already the tail, which is okay. This algorithm will still work. Okay? So there will be 3 steps for us to follow. Number 1, of course, we got to create a new node. So number 1, we're going to create a new node right here. And the node is going to contain the elements and also the next. Elements and also the next. You know what? I'll put elements. Oh, that's fine. That's fine. Elements and also the next. The element is going to point to wherever the parameter E is pointing to, right? You can see that's an element, right? What about the next? The next, for now, let's just put let it pointing to null, which is okay, just for now. Step number 1, just create a new node. And then step number 2, we can simply say the next reference here, rather than null, is now going to point to n.next. All right, let's do that. So what we do is we can say rather than pointing to here, it's now going to point to n.next. So this will be step number 2. And step number 3, we can try to say n.next rather than pointing to over here, it will just point to the new node right here. Step number 3. 3 steps. We don't seem to need any of the concept about previous node. So there's no linear operation or like a loop needed. So insert after is simply a very efficient operation, just about point like a references reassignments. So this is constant time, right? Again, we don't need to see the Java code to derive this. All right, question about this. Okay with this? So when we get to the final stage about summarizing the syncly linked list, of course, for all the operation that we have spoken about so far, we're going to put in the table. But if I give you anything like a new algorithm to define for linked list, you also got to think about what kind of cases are they involving. So you can judge whether it's going to be an efficient one or inefficient one. Right? Okay, let's talk about this one here. For this one here, if the node here is referring to this node, right? Let's say the node that's given as arguments is right here. Okay? The idea would be I want to insert a new node before that. That means whatever node that's really currently pointing to it is the next. Rather than pointing to there, it's going to point to here. That one does not seem to be an efficient operation anymore, does it? Not really. Because how do I know this reference here? I'm not given it. I'm only given n. In that case, I need to compute it myself using a loop. But I don't really know what the index is for that one. So I cannot really use get node at. I can still use a while loop. All right? That's a quick sketch. Right? Let's see exactly how we can do it. All right? If you're kind of sketching your mind about how the loop can be written, that's a good sign, but let's see. Somehow, I need to figure out what's the previous node right here, right? So you can think about this is the previous node that I need to compute, right? I'll get there in just one moment. That's one step for sure. And that step actually obviously is going to dominate the running time, as we'll see. All right? All right, let's now take a look. Step number 1, let's just create a new node first. Easy one. So step number 1, I'm just going to create some new node. Let me call it NN, new node, which will point to a new node object right here. And then that one there is going to get elements and next. Elements and next. You know what? Let me just move this a little bit up right here. All right? So the element is just going to point to wherever E is pointing to, right? Remember, E is right here, right? What the other parameter. What about the next? For now, let's make it null. Step number 1, very straightforward, just a new node. Step number 2, I basically have to make sure I got a node reference for the previous node. That's important before I can set this next reference, right? So step number 2, the most crucial step, is about computing the previous node. All right, and we need a loop. As I said earlier, we cannot really call get node at, which expects some integer number. We don't even know where this node is. Of course, what you could have done is figure out what this index is and say that index -1 and call get node at that index. That's fine, but there's a better way. All right. I'm just going to put a star here and then I'll put it here. you might just need to use a while loop for sure. And then remember the current reference, right? Let's say we got a current starting from the head. We want to run the while loop until current.next equals this particular n. Okay, of course, I really meant to say something like this. Let me explain this. Not equal to, all right? And of course, you have to make sure you say current dot, sorry. Here you got to do the normal update. You got to say current equals current.next, right? That's a standard updates. But let's analyze this condition here. Why would it work? If you look at this one over here, remember I mentioned last time, whenever you see a while loop, you always want to think about when does the loop exit. So that'll be the logical negation of the Boolean condition here. Let's take a look. That's going to help. So this one here tells you the loop is going to exit when this condition is false, meaning that rather than not equal to, it's going to be equal to, right? When the current dot next equals n. In that way, we know that current is indeed this previous node. Because if current dot next equals n, the current must be the previous node, right? That's how you write a loop. That's another flavor you can also learn. All right, any question about step number 2? That's the most fundamental step, actually, to make it work. So this one tells you whenever you want to somehow run a loop from the left until certain place for singly linked list, you don't necessarily always have to use an integer to tell you when to stop. Also, you don't really have to say current equals null or not equal to null to stop. This is just another example. It really depends what the problem is, right? So to really think about this one here, think more about the exit condition. This is going to help. All right. Step number 2. And we know that this while loop here, no way around. You may have to just go all the way until the end of the list, very close to the end. Linear time. All right. So this one here is going to be big O of n, because the previous node can be very close to the end of the list. Oh, let me just use this one here. All right, that's step number 2. And step number 3, now that I got a previous node, I can now just do the remaining task, just to set the references. Step number 3, I'm just going to say the new node next, rather than here, is now going to point to the n here. This will be step number 3. And step number 4, the previous node I got, I can now say its next should be pointing to this one here. Step number 4. And of course, at the same time, it's going to reassign this one here. So think about this is like a next. So this next is no longer there. After this, what kind of structure do we have? We have basically this previous node is going to point to the new node, and the new node is pointing to the n right here. So that's exactly insert before, right? We're inserting this new node right before this node here. And that's a linear time algorithm, because the critical step number 2 is linear. All right, any question here? So when you, just before you ask, okay. So when you review these 2 operations, you really want to ask yourself, why is insert after constant, but insert before is actually linear, right? As we explained. Yeah, question?
How do we do if the insert before, you want to insert before the very first node?
Insert before the very first, it will be very similar. So let's say insert before over here. I see what you mean. That will be a special case, right? So here, very good question. So insert before, this is more talking about the previous node happen to be not null. And if you want to insert before, that's even easier. If you want to say, I'll put it here. Insert before the first node. In that case, you can just add first, which we know how to do, like an edge case. Good. All right, guys, any question about this? Good? All right. So we are done with all the operations that I want to discuss about singly linked list, but let's now take a very quick look on some exercises I want you guys to also try. Of course, these two, you want to put them into Java code. And also this one here, you can think about how do I implement remove at. All right, I want to remove the node at index I. Sounds like a linear time operation because there's no way around. I have to get to some node in the middle. But should I go to I minus 1 or should I go to I? You guys decide. Okay, think about it. All right. Given all the operations we have set so far, it should be possible for you to judge. For implementing remove at index I, for removing a node at index I, should I get node at index I or should I get node at index I minus 1 or some other index? You want to think about that. All right, let's do a very quick comparison and we can take a very short break. Right? Today we can take a few short breaks since there are many things to cover. So I want you guys to reset after some short break. So before the short break, let's talk about this table here. We are going to compare arrays and singly linked lists based on what we have said so far. So should you memorize the result for this table here? I don't think you should really memorize it, but you should really, when you study for the singly linked list, look at this table here, look at the template that's blank, and think about each one of them. Think about the reason for the asymptotic upper bound, right? Which is what I'm going to present right here. Let's first of all think about if I want to get a size or get a first and last elements. In the case of array, pretty easy. Array.length. Also at index 0, at index length minus 1, indexing, cheap, efficient. How about singly linked list? I can get to the size attributes, I can get to the head, I can get to the head, I can get to the tail, right? So all efficient operations. So for this one here, I can simply say big O of 1. That one's easy, all right? And let's talk about array first before, and then we move on to linked list. For array, if I want to get to index I and also, okay, so here when I say remove the last element, let me clarify. What I really meant there is something very simple. So for the array, I really assume we don't do any resizing. We simply say A at index A.length minus 1 will just be assigned to just now without resizing it. Pretty simple operation, right? So that's why it's constant time. But of course, if I tell you that resizing is necessary, it will be linear. Right? So for these two, for array, it will just be constant. And if you want to add the first elements, that will involve some shifting, right? All the way to the right by one position. Also, if you want to remove the first element, you're also going to shift everything to the left by one position. So that's going to be expensive, linear time. Add remove anywhere in the middle is also going to cost you linear time, right? So for the array, we said that it's always expensive if you want to touch, somehow get rid of some element in the middle or in the beginning or at the end. Linear time. Let's talk about singly linked list. Whatever that's actually cheap over here turns out to be expensive for singly linked list. For example, if I want to get element at index I, get middle, linear time. Right? What about if I want to remove the last element? Also linear, because I need to get to the second last node, right? Big O of n. So for every one of them, we also talk about, so you want to make sure go back there and review the rationale. Why? For example, removing the last will be linear time. And then when we want to add or remove somewhere in the middle, if somehow we can get some reference. For example, let's say here, I want to insert before, but I'm given, I want to insert after. For example, like right here, if I'm given the node itself, I don't need to compute the node by myself. So I'm given, so it will be a constant time operation. It's just all about references, all right? So the critical distinction over here will be, so this one will be actually constant time because I don't need to compute any of the nodes. There's no need to compute the node if they are simply given. On the other hand, if they are not given, then you have to compute it yourself. Maybe the node before, or maybe the second last node, and etc. All right? So symmetrically, it's going to be big O of n. Right, so that's the complete table for comparing. All right. Any question about this? Yeah, use this table here to somehow summarize about everything we have discussed so far about arrays and linked lists. It's a very nice way to kind of reflect on what we have learned. All right. If no further question, why don't we take a 2 minutes break and then we'll just come back for doubly linked list. Okay. All right, so we are done with the singly linked list, and we're going to move on. Oh, by the way, slide 33 to 36 about the generics, which I assume you guys have already studied. If you haven't, please catch up. It's required for your programming test as well. Okay? Let me know if you got any trouble following the material I gave to you. All right, let's now talk about doubly linked list. Before that, let's have a final recap about singly linked lists. Okay? So we pretty much know, before the break, we actually did the table, but now let's put it in the textual form. So you got to remember what singly linked lists really perform well versus poorly. All right, you can look at the bullet points. We have already said everything. What I want to draw your attention to is about this one here. Whenever you want to insert or delete from the middle, if you're somehow given the reference to the previous node, then good. It's going to be constant time. If you are not really given as a method parameter, then it will be linear time, right? That's something you want to watch out for, all right? And we're going to see that principle about trading space for time one more time to see how we can somehow introduce some additional attributes so that some of these operations right here, some of them, is going to be improved drastically from linear to constant. But I'm not saying that having that little extension is going to magically turn everything from linear into constant. In that way, nobody's going to use singly linked list, right? There's only going to be one or two operations that will be a little bit more efficient, right? That's something we'll see. All right, so we're going to introduce new attributes just like how we introduce size and tell. We'll get there, okay? Let's now talk about doubly linked list, okay? So for doubly linked list, let's go over some visual introduction here. Okay, right here. All right. It is still going to be a chain of nodes, but now the direction about referencing is going to be bidirectional. Rather than just next, we're going to see another reference called previous. And we need to visualize that before we see the Java implementation. So the bidirectionally connected, bidirectional here is very important, right? So let me show you some very quick diagram. In the case of the singly linked node, SLN, right? I want to distinguish between singly linked node and doubly linked node. Each node has only two compartments. We have the elements, and we also have the next. So there's always single direction. You always go to the right, right? But for doubly linked node, we're going to introduce one more direction, which is conceivable, to the left. So doubly linked node is going to look a little bit like this. A little bit bigger because it stores more data. The convention is in the middle, we still try to put a reference for the elements. And then the next one here is going to be next, going to the right. And the new addition is we're going to have something called previous. Right? PREV. Okay? That one will allow us to travel backwards. Okay? And you can right away imagine if this node happens to be the tail, do I still need a loop anymore to calculate the second last node? Not really, right? I can just go to the previous. That's immediately going to make it from linear into constant. All right? So that's something you want to see right away. All right? So what we get is we got the data object. Okay. We got the data objects that already also the next. So these two are the attributes that are already in the singly linked node. We are making the extension about previous node right here. So that's the extension. Okay. And then let's see a little bit more visualization here. let's see how the object structure is going to look like. Okay. Let me see this right here. Okay, let me just present maybe a little bit more bullet points from the slide, and I'll do the visualization right here. So we talk about the two references to the data and also to the next node. And also we got the previous node reference as well. All right, so this is also another important point. So if you want me to summarize about how many extensions do we need in order to have a doubly linked list, two extensions basically. The one we just talked about is the previous reference. So here comes the second extension. And the second extension is really because in the singly linked list, we have to deal with edge cases explicitly too often. That will somehow make our code structure more complicated than necessary. So we want to simplify the code structure. Nothing to do with performance really, but it's good software engineering principle to really keep your code as simple as possible. And let me give you some example. In the case of the singly linked list, let's say add first, right? You actually have to consider if the current list is actually empty. In that case, you have to deal with it explicitly. Tail should be equal to head afterwards. Similarly, let's say you're trying to do remove first. In that way, if the current size is equal to 1, after removing the first, the list becomes empty. In that case, you have to explicitly say the head and tail will be null. It would be very nice if we don't really have to write these two if or else if explicitly. There is a way to achieve that by some small extension in the doubly linked list. We'll see that. All right. All right, let me show you the extension very quickly, the bullet points, and then I'll visualize them. Okay. Header and trailer. All right, so whenever we talk about header and trailer, so these are the concept for doubly linked node. Sorry, doubly linked list, not singly linked list. In the case of singly linked list, we got head and tail. By doubly linked list, we got header and trailer. Right? Notice the difference here. Also, the wording is a little bit different, right? Header and trailer. And sometimes people like to talk about them as sentinel nodes or guard nodes, right? Just terminology, right? But I might just call them header and trailer. So these two do not store data. Okay, I'll visualize it, and also, okay, and etc. They always exist, even in the case of empty list. So now let's clarify visually. Let's now get to visualizing empty list, either singly linked or doubly linked. Let's see exactly how they will look like. If we talk about the empty singly linked list, which we did earlier, but let's brush up quickly. So what you have is you got list number 1 pointing to this object here. So we got singly linked list, and we got a head, and we got a tail, and also we got a size, right? So these are the 3 attributes. Size will be 0 for the empty list, and also we got a head and tail being null. Right here. That one's straightforward. We have covered that already. What about empty doubly linked list? It's a bit trickier, right? The header and trailer are not going to be null. They will be pointing to some node. That's the tricky bit, right? But you'll get used to it. So empty doubly linked list. Right here. So let's say we got list number 2, which is a different type. That one there points to a doubly linked list objects. And we also got 3 attributes for doubly linked list. We got the size, we got a header, and we got a trailer. Okay? Let's see how they will look like. So we got something called a header, we got something called a trailer, and we got something called a size. For the size, again, 0. Okay? That's a list level. At the node level, we got 2 doubly linked nodes. I'm going to draw that here. So we got the first doubly linked node right here, and we got a second one. 2 of them, right? And the first one there, we got a previous, and we got a next, and also we got a previous, and also we got a next, right here. To start with, let me just show you which one's header, which one's trailer first. Let's say this one here is pointing to the header, the first one, right? That's a header. And this one here is the trailer. At the list level, they just always point to two nodes, header and trailer, always the same. You don't change header and trailer, never. You don't change them. What's so special about header and trailer goes like this. They don't store any meaningful data, meaning that the elements fields will just be pointing to null. That's the elements. And the element also point to null. And in the beginning, when the list is empty, header and trailer simply point to each other somehow. So the previous of the trailer is going to point to the header. And the next of the header is going to point to the trailer. Think about this is the next. And this is the previous. And what about the previous for the header? There's going to be nothing before the header. So it's going to be null. Also, there will be nothing that's after the trailer. So that one there is going to be null. This is a very important visualization for you to see, right? Number one, they're always the header and trailer nodes, and they don't store any meaningful data, and they are interconnected with each other. As you introduce more nodes into the doubly linked list, we're just going to add some nodes in between. For example, we might add a node here in between. We're just going to set the references appropriately, which we'll see how to do it. Okay. All right. Any question about this? Right here. Yeah.
Since the doubly linked list has this similar functionality to the single linked list and more, would it be advised to always use it in all scenarios, or would there be scenarios where you have to use the single linked list?
I would say you can say a singly linked list is almost like a doubly linked list. But the doubly linked list is going to introduce some extra attributes that's going to make certain scenario that's going to perform better as opposed to like a singly linked. Well, I would say if you have a choice, how about that? You should always use doubly linked list. Yeah. Because whatever that's going to work on the singly linked list is also going to work on the doubly linked list because you always got the next reference. Yeah. Right? But there will be a certain situation you will be able to exploit the previous reference to make some operation more efficient. But interestingly, usually when you're getting some interview problem, let's say it's for some tech company, usually they like to use only singly linked list. They don't like to use doubly linked list. Yeah, but just keep that in mind. If you really have a choice on your own, always choose a doubly linked list. Also, there's a catch. I'll get to you. Okay. It's actually harder to code with because you got to think about what references you got. Right? Also, you got to update the header and trailer also appropriately. Okay, Diego.
So you mentioned that the header and trailer always exist even if the list is empty.
That's correct.
Okay. So does that mean that, for example, if you wanted to implement a method like add first, technically we will never be adding a node as the header, but rather.
Okay. How about this? Hold that question there. We'll definitely get there. Okay. But what Diego was asking is about somehow. Okay. How about it? Let me hold this question here. I'm gonna do one more visualization. That'll be clear. Okay. The confusion might be, well, if the header and trailer are already here, what about the content of the list? That's something we're gonna figure out. Okay. Let me just do one more diagram, which I plan to do anyway. Okay. One more. And for this one here, I just need 7 nodes to really illustrate the idea. That's built from scratch. That one there is going to make it very clear about which part should be part of the list and which part is basically just for guarding. Okay, so I'm getting 1 here. Bear with me. And then 1 here. And also 1 here. Okay, I'm also going to get 1 here. Okay, and then this one I can just copy right here. All right, and then I'm just going to say ... right here, which means there might be some arbitrary number of nodes in between. I just make it very general. Okay, and here I also got ... Let's say this is index I. All right. So we're following the same convention as before. The first node is going to be index 0, index 1, and maybe somewhere in the middle is I. All right? And then the last node is going to be n minus 1, and then n minus 2, right? Like that. And what about the other 2 nodes at the 2 ends? They are the header and trailer. Header right here. let's use, oh, sorry. Let's use this one here, header, and also trailer right here. Okay, header and trailer. Let me annotate it and then talk about their indices. Header and also trailer. Interestingly, header you can think about has the index -1. Trailer has the index n. They are both not valid indices for indexing. But conceptually, that's how you should think of it, which is convenient because whenever you think about if I want to get to index -1, it doesn't make sense. Of course, because header and trailer are not simply part of the list contents. All right? Just keep that in mind. You want to think about basically this part is the contents of the list. Contents of the doubly linked list. All right? And then let's now try to build a pointer very quickly. Okay? References. So for the header, it has nothing before that, so previous is going to be null. And it stores nothing meaningful, so data element is going to be null. And its next is going to point to the first node right here. Symmetrically, for the trailer, also it doesn't store anything meaningful, so the data element is going to be null. And nothing is going to come after the trailer, so the next is also going to be null. So let me move this n here, right here. All right, index n. And that one there should be null. And then the previous reference of the trailer should really point to the last node. Okay, let me just write it down more explicitly for you. The header dot next versus the trailer dot previous. This one here is really the first node. And this one here is really the last node. I wouldn't encourage you, but it may help to think in this way. Think about the first node here is like the head that we spoke about earlier. And this guy here is more like the tail that we spoke about earlier. But if you think that way, I'm just worried that you might get confused between the two lists. But anyway, if that helps. Okay. All right, let's now try to build other references, right? So we may have, let's say for the next reference, so let's say here we got a next, right here. We got a next, point to some other nodes, and some other node point to node I, and also node I point to I plus 1, and some other nodes point to n minus 2, the next reference, and point to here, and that one there will point to this one here. It's all about the next references, right? They just get interconnected, right? That's one direction. Of course, whatever you used to be able to do for the simply linked list, you can just go all the way using next reference to the end. No problem, all right? Now, you got the other direction possible for you, okay? So you might use the previous reference. Let's say here, it might just say previous over here, and then I can also do previous again. So maybe from the last node to the second last node, right here. From the second last node to the third last node. And from some other node at index I to node at index, so this will be from index I plus 1 to index I. And then from the third node to the second node. And from the second node to the first node. You know, you see the idea. So these are just the previous references, right? And here as well. That's the most general way you can think about what a doubly linked list is. All right? So that's about visualization. And I'm building all these up to talk about right here. What about getting access to different parts of the doubly linked list? Let's see if that might improve anything. Just before I get to you, let me finish this. Okay, I'll point to you. Okay. If I just want to get access to the beginning and the end. So let's say I want to get access to, let's say right here, the first node. And also I want to get access to the last node, right? It will just be header.next and trailer.previous. Attribute access, big O of 1, right? both of them will just be big O of 1. Big O of 1. That one's easy to see. But now, what about I want to access somewhere in the middle? Let's say I want to access somewhere in the middle. Maybe let's say it's I. Right here. This node, right? So here, for this one here, is somewhere in the middle. What will be the worst case? The worst case is, you might be thinking when I is exactly n minus 1, I can definitely go for one previous reference, or I can go for another previous reference. That's true, but when I is getting to the very around the middle, let's say n divided by 2, asymptotically, it will still be n. Right? Similarly, you might be thinking if I is very close to the beginning, and I can just use next reference. That's true, but when I is very close to the middle, you still cannot get around. It will be asymptotically, in the worst case, linear time. When it's around the middle, about n divided by 2. So if you try to do a big O, it will still be big O of n. So what this means is, even though we have introduced the header and trailer, we have introduced the previous reference, it will not improve how you access the middle of the list. It's not going to work just magically to make a constant time. All right? That's important. Yeah, sorry, you got some question.
So, if the header and trailer are similar nodes, what we have in the list, why aren't they part of the list?
Because header and trailer don't store anything meaningful, right? The reason that, which you will see a little bit later, very soon. The header and trailer conceptually are not really part of the list because they don't store anything meaningful. Let's say we got a doubly linked list of person. They don't really store the person over here, so we don't really count them as part of the list contents, right? So these nodes are there to make our code writing easier, which we'll see. Okay, yeah. All right, I apparently forgot to put one more reference here, right? Just my, all right, right here. Okay. All right, guys, I think this one here is a very important visualization. We try to show to you how you can build from scratch some header and trailer and also somewhere in the middle. And the next step will be we're going to see exactly how we can build the doubly linked list in Java. Okay. All right, so here, and this slide here, slide number 41, somehow just kind of summarizes about the two extensions we have for doubly linked lists from the singly linked list and try to explain their rationale, which we already discussed. But I'm just going to write one more page just to summarize a little bit more briefly. But you can also review the slides as well. Okay, right here. Okay, so why do we have the doubly linked structure? So why do we have doubly linked list or doubly linked node? Be very careful. You want to know which extension is at the list level and which extension is at the node level, right? Why? Okay, it's a brief summary. Number one, for asymptotic performance. And for the performance, for example, we want to make the remove last more efficient. Because to get a previous node, like a second last node, we can just say trailer, the previous, which will give us the last node, and then previous, which will give us the second last node. So this one here is going to be the previous reference that we introduced for doubly linked node. That is the extension at the node level. And the second one is about the code structure. Nothing to do with performance. It's just about writing better code, which we'll see right after this. All right. The code structure is what we introduced for the header trailer for doubly linked list. Okay, so this one here is going to be the header and trailer. For the doubly linked list, right? And let me just emphasize one more time so that we don't need to handle edge cases explicitly, like what I showed to you in the singly linked list example. That means we don't need to handle edge cases explicitly. Right, quick summary, but you're going to see more detail on the slides and then also from our discussion, right? It's a quick summary for you. Right, any question? That's conceptually about what you should know about doubly linked lists, but the rest will be to see some Java code and how we can build some list. Okay, let's see. Let's start from the basic. Let's see the class that we have. So we got two classes over here. We got the doubly linked list class right here. And guys, notice that it's generic, right? Which we expect you to know, right? From the required study, right? Got to catch up with that. And also we got the we got a node here, right? We got two classes right here. Both are generic. Let's now see the attributes. At the node level, as we said earlier, we got elements, we got the next node, and also we got the extension for the previous node, which I'm going to highlight here, right? You can see node here. Right, we got elements, we got next, we got previous, right? Oh, also, we got a conceivable, accessor, mutator, etc. Right? So these are all basic. What I'm going to show to you later will be how to use this constructor, right? The convention, which for the in-class example, whenever you're constructing a doubly linked node, you always pass the reference for element first, and then followed by the previous, and followed by the next. All right, that's a convention. We're going to use that quite often in the example we're going to discuss today. Right, we're going to look at the constructor a little bit later when we see the example, right? Just highlight it for you, right? And then we have right here, for doubly linked list, we got attributes like, let's see here. We got the size, also we got the header, and also we got a trailer, which we discussed earlier, right? So these are the three main attributes we have. And of course, we got other methods, which we'll speak about very soon. And also, we have this constructor right here, doubly linked list. And we're going to go over this code here line by line very soon, all right? Very simple structure, right? Let's now consider this test case right here, right? We're just going to trace how exactly we can create an empty list, which is important, right? So let's see how we can do that. This line, all right? So apparently we are trying to create a list pointing to doubly linked list. Right here, okay? Doubly linked list. It's a doubly linked list, and we are storing the string element. By the way, you can see string is instantiating the E, right? How you use the generics. String, all right? And we got the header, trailer, and size. So let me put size right here. And also we got header and trailer. Trailer. Right here. All right. Size, by the way, if you look at the constructor for the doubly linked list, we don't really mention that. So you will just get the default value 0. That one's obvious. Let's now take a look at these three lines, one by one, and see how they work together. All right? So let me say this will be step number 1, and this will be step number 2, and this will be step number 3, right? That's exactly how they work, right? Step number 1. You can break it down into two parts. We are doing the right-hand side, create a new object first, and then we try to assign that into the header, right? Let's do that new node first. And I'm just going to copy this one here, which I can reuse, all right? So we're creating a new node right here, right here. So this will be step number 1, creating this new node. And then you can see the null, null, and null. All right? That means the element is going to be null. And the previous is going to be null. And also the next is also going to be null. And then we say that the new node is going to be assigned to be the header. That means our header of the list is going to point to right here. This is what step number 1 is going to do. All right? So on the right-hand side of the equals, we are creating this new node. On the left-hand side, we're trying to assign this new node as the header. All right? And step number 2, very similar. Step number 2, we're basically doing two things. You got to watch out. Because on the right-hand side over here, you can see we're still passing now as elements, now as the next, but for the previous, we got a header here. Watch out for that, okay? So I'm just going to create another new node right here, okay, here. So the now here is about, oh, sorry. So the now here is about the elements. And the header is basically the next. So that means, sorry, the header here is the previous. Beg your pardon. This is the previous, okay? So that means the previous is going to be whatever the header is. You can see currently the header is pointing to here. That means previous is also going to point to here, all right? It's going to be right here, the previous. And then the next is going to be now. Oh, no. And don't forget, we also got this variable assignment here. Whatever the new node is, the trailer is going to point there. All right? The trailer is going to point over there. All right? That is the trailer. So this entire thing will be step number 2. All right? Finally, step number 3. We are simply setting the header next to be trailer. Right? Basically, we're saying header dot next currently is null, but we want to make sure it also point to the trailer right here. Right? Trailer is already here. Right? So they point to each other. Rather than now, it's now going to point to right here. So what's the structure we have built? We basically have built something like this. So we got a header pointing to right here. That one there points to the trailer. And the trailer also points to this. Exactly the structure that we saw earlier before the break. Well, right here. Okay? Very good. And one more thing to show to you very quickly, right? If you look at step number 2, right here, I'm going to highlight it. If you don't quite like, for example, this particular one, you got to pass a header, it's okay to split it into 2 lines if you want, if you wish. Okay, I'm just going to write here. So step number 2 is equivalent to, if you simply say the trailer is a new node. And then it's going to store just null, null, and null. And I'm just going to set a header separately, right? And then I can say the trailer dot set previous to be the header. So this pointer over here is basically, you can see trailer dot set previous. Trailer is this node. Previous should be basically whatever the header is right here. Right? We're just doing that separately. You should really understand both. They are equally effective achieving what we want, but whatever you write in the programming test or assignment is okay. You can choose either way. That makes more sense to you. All right? All right. That's different ways of writing the same thing, really. Okay? Any questions about this? Okay, very good. So let's now move on to, okay. For the rest of the lecture for today, including some extended 10 minutes, right? Again, I will break around 6:50, so for those of you who cannot stay longer, feel free to leave, but just got to catch up the last 10 minutes. For the rest of the class, I just want to show you 2 very useful helper methods. Helper method number 1, addBetween. Helper method number 2 is called remove. Once we got these 2 helper methods defined, everything else regarding insertion or removal can just be about calling these 2 helper methods. And the reason why we can do this is thanks to header and trailer. Right? That's a roadmap. So I'm definitely going to go over with you in detail about addBetween and remove, and I'll hopefully give you one example for each. Right? So, and then the rest will be some exercise for you to really do the tracing and also some understanding for you, by yourself. Right? They're pretty straightforward. All right? Let me now do the addBetween. All right? So this is a mutator method, addBetween. By the way, it's a doubly linked list method, okay? So we got addBetween, and then we want to add a new node. And the new node is going to store some element E, and then we got something called predecessor. We got something called successor, all right? And we have some assumption here. Because if you want to say, this is the predecessor and this is successor, I want to add something in between. Then the assumption is the next of the predecessor must be the successor. And the previous of the successor must be the predecessor. They point to each other, basically. All right, that's the assumption. The assumption is that we got predecessor dot next equals successor dot previous. Symmetrically, we also got the successor. Oh, actually, that should be good enough. Okay, beg your pardon. Okay. Oh, let me just, sorry, I'm not, beg your pardon. Let me say that again. The predecessor dot next should be the successor. That's what I meant to write. There we go. And the successor dot previous should be predecessor. That's exactly what I meant to say. All right, so that's the assumption we have. All right, you can think about that Boolean condition there. That's exactly telling you this structure over here. All right. And let me just highlight one more time. So we got predecessor, which is over here. We also got successor, which is over here. Now, how do I add a node in between? Let's now go over the step. Basically, you got to add a node here and make sure point something like this. Let's say exactly each step. So let's say we got step number 1 right here. We got step number 2 right here. And we got step number 3 right here. Only 3 steps. Of course, you can think about we got to increment the size as well. That was easy to see, right? Just increment the integer. Okay. Step number 1, the blue one. We're going to create this new node. Right? It's going to be a doubly linked node. I'm just going to put it here. Somehow this node is going to be added between the predecessor and successor, right? So we are saying that if you recall, this is the elements, and this is the previous, and this one here is the next, right? It'll be very obvious. So for this element here, the element is going to point to wherever E is pointing to, okay? And the previous is going to be the predecessor right here. And the next is going to be the successor. And then this is something we call the new node. Let me say NN, new node. All right, that's line number 2. And then line number 3, we are actually going to set the predecessors next. Rather than pointing to over here, it's going to point to the new node. Then it's going to point to right here. Okay, right here. And the next line, for the successor, we're going to set its previous. Rather than here, it's now going to point to this new node. Okay. Let's see some highlighter just to see what the new structure is. So we don't have this we don't have this connection anymore. So what we have is something like this. So we have the predecessor right here, and it points to this node first, and that node points to this node here, the successor. Symmetrically, we also got the successor got its previous point to this node, and that node got its previous point back to the predecessor, right? We got a symmetric references between the two, right? This is the helper method for addBetween, and we are claiming that I'm claiming that for all the insertion related methods, we can just call this guy here as a helper method, as long as we can define or identify what the predecessor is and what the successor is. Okay, keep that in mind. All right, let's see. I think I got 2 minutes over here before 6:50. So why don't I just go over the remove very quickly, right? So the rest will be just an example in 10 minutes. Okay, let's now do that, remove. Okay, that'll be the second helper method. All right, the second helper method here is going to be also very similar, but in some ways simpler. We want to remove a particular node in the middle of the doubly linked list. So we don't need to add any element. So there's just a single node as a parameter. So what we got is we got this node here, and that's the node we want to remove. Very easy to see, right? If I want to remove this node here, what should I do? Well, this node should be completely detached from the chain. The next should be set to here, and the previous should be set to here, right? That's it. Okay, let's take a look. All right, let's just be precise about how this can be done, and then we'll take a very short break, and then we'll go over some example, and we're done. So what I will do is I'm first of all going to talk about predecessor and successor. Okay, let's identify them first. I'm given this particular node. This is the node I want to remove. So this node previous will be the predecessor. And this node next will be the successor, right? That's basically these two steps. So this will be the predecessor. And this will be the successor. So think about this is line number line number 2. This is line number 3. All right? Once I've defined these two references, everything else will be very, very easy. Let's go over one by one. So I got blue, I got green, I got orange, I got pink. Okay, quickly. Okay, bear with me, about 1 minute. So, predecessor that's set next. Rather than pointing to over here, it's now going to point to the successor, right here. Next one. Successor that previous, rather than here, is now going to point to the predecessor. And then I want to make sure this node here is also completely detached. So the way to do that would be, so for this step over here, the node that's set next, null. And also the node that's set previous, also null. Right? So these are all the steps. Of course, you decrement the size value as well. So the new node structure goes like this. So we got the predecessor points to directly the successor. Symmetrically, we got the successor points back to predecessor. And you can see this node here is completely detached. That's how we remove it. Similar idea. This helper method here can really work as a helper method for any removal related like a method, as long as you can identify what the predecessor is and what the successor is. Okay, and I'm just going to let you guys take a 2 minutes break. If you're able to stay for 10 minutes, please stay. Otherwise, no problem. You can watch the recording later. Okay, so before the break, we basically spoke about these two helper methods, right? We talk about remove and we talk about addBetween, right? So the claim will be once you got these two helper methods, any subsequent methods about insertion or removal can simply call them as helper method. I'll give you one example for each, and then for the rest on the slide and on the iPad pages, you guys have to try as exercises, right? The idea will be very similar. Again, the very important idea is really to identify the predecessor and successor, and that'll be it. Okay, let's see. Let's see one example for addBetween. Okay, let's say I want to declare I want to implement add first. Of course, if you go back to the definition for add first in the singly linked list, you got the edge cases to deal with explicitly. But now you don't need to for doubly linked list. I can now just call addBetween. All right, add first. And what I need to identify would be something like this. First of all, of course, you're going to know the elements that you want to add into. And I claim that the predecessor I need will be just the header. And remember, successor should be the next of the predecessor, right? So that should be header again next will be the successor. So this will be the predecessor, and this will be the successor. Of course, if you want to really call this addBetween as a helper method, this is something you have to identify yourself, right? let's see how we can visualize this. Okay. So let's say we actually got this doubly linked list already created. That's empty. All right. Oh, sorry. So we got this line here, which has created right here. There we go. So this one here has created this doubly linked list as empty, right? We'll talk about header, trailer pointing to each other. According to this addBetween over here, right? So we're going to do the first one right here. At first, mark. What that would do is it's going to look at predecessor right here as the header, right? You can see header is pointing to here. So this will be the predecessor. And predecessor.next will be the successor. So here currently the list is simply empty. So predecessor.next just happened to be the trailer, but may not be true in general. If the list is not empty, header.getNext will just be the first node, right? So it depends. So this is the predecessor. Its next will be right here, the successor. All right. So once we have identified the predecessor and successor, what's going to happen? Well, what's going to happen will be just like how we define over here. You can see the predecessor here and successor here. And we just do all the steps that we said earlier. Right? Okay. And for that one there, let me just do that quickly. And then I'll let you know what exercise you can do. I'm just going to put that node right here. Okay, that's the node. And then you got to follow all the steps that we had earlier about here, right? So you create a node, and the element is just going to be, in this case, mark. The next should be pointing to the successor, and the previous should really be pointing to the predecessor, right? And then we are also going to remove these two links. Agree? Right? Yeah, and then we're done, basically, right? So if you look at the lines here, that's exactly what we did, right? So what we got to do is, okay, just one more thing. This one here, of course, we're going to set the next to be this new node. And we set a previous, rather than here, is going to be point to this node. That's what's left. The new structure is going to look like the following, all right? So we got the predecessor right here. Its next is pointing to this new node. And the new node next is pointing to the successor, right? And if you go backwards, you go from successor, go for its previous, you go to this new node. And then the new node previous go to this node here, right? That beautifully actually defines the add first using predecessor and successor. All right. So that was one example about how you can call this addBetween as a helper method. And your exercise will be try to trace another add first by identifying the predecessor and successor. Why don't we do that very quickly? Given that we got 1, 2, and 3 nodes, of course the contents will just be this. In that way, if we want to add first, what will be the predecessor? Still right here. Oh, sorry. The predecessor will still be just the header. And the header.getNext will be the first node that we have added, right? So now predecessor, successor, we can add a node in between right here. Okay? That's basically what you got to do. And then your exercise will also be try to trace add last right here. And for the add last, you will see the way we define, you'll be symmetrical. The predecessor will be, and the successor will be just the trailer, and the predecessor will be that one that get previous. Right? You gotta really see that in the diagram and work out the logic. That's predecessor. Okay. Guys, any question about this? We okay with that? Yeah.
So, like in the calculations, like
Yeah.
adding or removing anything,
Mm-hmm.
we take the header and the trailer, but while accessing the data, we just take this, like that's the real data.
So, sorry. So guys, sorry. Yeah.
That's the real data, like the.
Can you say the question again? Sorry, I didn't get it.
So while removing or adding,
Mhm.
if we are like adding at the end or
Yeah.
removing from the start,
Mm-hmm.
then we consider these two nodes,
Yeah.
the header and the
Yeah, for sure. So depends on which end you want to add, right? You want to add maybe closer to this end, so this will be the predecessor, and the next one will be successor. If you're adding maybe around this end, in that way this will be the successor, and the previous one will be predecessor.
like for while accessing the data, somewhere in the usage.
But accessing will be another operation, which we don't really use addBetween, right?
Consider these two nodes, like any
No, yeah, exactly. So whenever you want to access the data, you don't really access data for header or trailer. They are simply just null, right? Okay. All right. And one thing to mention, if you want to say add, right? For this one here, exercise for you, you can really try to trace the code, but you can also see addBetween. This will be the predecessor, successor. You can actually see, right? It's at the implementation here. But what about asymptotic upper bound? Since we are trying to call get node at I minus 1, again, we're running into linear time operation. This tells you if you actually want to execute the add, even for doubly linked list, you will still be linear, no way around. But what you want to pay attention to will be predecessor, successor, how they are calculated and passed into addBetween. Right? That's something you got to do. Right? Exercise for you to try to trace them. All right? Exercise. Okay, right here. All right. Okay, I think we got 2 minutes. Let's see if we can just do one more. Okay, just one more, please, very quickly. All right, so for this one here, I just want to do the following. So after adding first for Mark and Alan, we got Alan and Mark right here, right? I want to say I want to remove first right here. Remove first. Okay, let me finish this one, and then that'll be it. Okay, whatever that's left, I'll do that after reading week. So remove first, if you look at that, is actually going to be right here. Remove, calling that method there. We just know what we want to know which node to remove, right? How do we get to the first node? It will be header.getNext, right? Header.getNext. So this is the node to actually remove. And if you go back to the remove definition there, we can calculate predecessor and successor, right? Getting the previous, getting the next. So what we get accordingly will be, this will be the predecessor, and this will be the successor. And how do we conceptually remove this node? The way to do it would be, we're going to reset the references. Predecessor.next, rather than pointing to here, is going to point to successor. Successor.previous, rather than pointing to here, is now going to point to the predecessor, right? And also, we're going to reset these two references to make sure this node is completely detached, right? So what's really important is you got to pass the node you want to remove. And the helper method is going to identify the predecessor and successors accordingly, all right? Finally, give me 30 seconds, I'll let you go. So your exercise will be trying to really trace, let's say, this one here and these two as well. See how they are passing the argument to the helper method to see how they work, right? That will be an exercise for you. All right. So what's going to happen is after the reading week, we're going to start with this page just to finish off all the topics about linked list, and we can move on. And during the reading week, I'm going to send you some references. If you want to go over the exercise, want to see the solution, there are some videos to help you if you want to go over the solution. All right, thank you so much, and then I'll see you after the reading week.